Hello and welcome everyone to this podcast for cell biology. In this podcast, we're going to talk about enzymes. Now, most enzymes are proteins. Now, some are RNA molecules. And when that's the case, we call them ribozymes. Now, we've talked before about proteins. And remember, proteins have many functions. But one thing they all share in common is that proteins always bind something. Or I should say bind another molecule. And so enzymes are no different. They also bind other molecules. However, they do so in a very special way. So let's talk about that. So let's draw kind of a generic looking enzyme here, where this is our enzyme. And this here, inside here, this opening here, that is our active site. What binds into this active site is something called a substrate. Now there could be multiple substrates hanging around outside of this enzyme, and each enzyme is specific to one substrate. Enzymes don't typically bind more than one substrate, and they'll bind it with precision. So for instance, in this generic drawing here, only this triangle is going to effectively enter into this active site and bind to it. These others may bind to a different enzyme. They're still present, but only this substrate here will bind into this active site of this enzyme. So these are substrates. Now sometimes, as a generic term for something that binds to a protein, we call those ligands. But when we talk about enzymes, we're talking about substrates as the specific ligand that binds into the enzyme's active site. Okay, so now let's draw this substrate in the active site. When this substrate binds into this active site, something will often happen, and that is that this enzyme will change its shape a little bit to more tightly bind to it. So what I'm going to do is I'm just going to kind of fill in these areas here, just to try to demonstrate that once it binds in there, it locks it in there a little bit more securely. So what we call this in general, when an enzyme or any protein changes its shape, we call that a conformational change. It's a word we use a lot when we talk about the function of proteins. And when we're talking about the function of an enzyme, we more specifically call this conformational change an induced fit. And we've talked a little bit about this concept before, and that is the concept that enzymes and proteins in general, but specifically for right now, enzymes are not rigid, but rather flexible. So now let's ask this question. What causes the induced fit? Well, when that substrate enters that active site, what occurs are a series of non-covalent interactions. More specifically, hydrogen bonds, ionic bonds, and hydrophobic interactions. I should also include our good friends van der Waals. Now remember, each of these bonds by themselves are not super strong, but together it allows for a very strong interaction with this substrate and the active site to force this induced fit. The types of non-covalent interactions and the number of non-covalent interactions helps determine substrate specificity. That means which substrate will bind to this active site is strongly dependent upon the types and the amounts of these non-covalent interactions. So once that substrate has bound to the enzyme, what does it do next? It's got to do something, otherwise why would it bind? So let's spend some time talking about what's going to happen after the substrate binds. And to do this, let's think about a more real-life example. Okay, this enzyme, let's call it a glucokinase. Gluco, because it's going to bind a glucose molecule, which we're going to draw like this, and it's going to bind an ATP molecule. Kinases are enzymes that will catalyze the transfer of a phosphate group to another molecule. So what happens here is our glucose molecule is going to bind, say right here, and then our ATP molecule is going to bind right here. Now remember what we said before. What happens is that there will be a conformational change that occurs that will cause this induced fit that will bring these two substrates closer to each other. And so let's try to draw it like so. So it's changing its shape, giving it that induced fit. And by doing so, what it does is it brings this ATP molecule closer to the glucose molecule. In doing so, it helps facilitate these two molecules' interactions. It helps move this phosphate group from ATP over to the glucose molecule. And once this ATP has transferred the phosphate group to the glucose, it once again causes it to change shape and releases the glucose. But now the glucose will have a phosphate group on it, and ADP, which is two phosphate groups, is released. One might argue that glucose and ATP at some regular interval in the cytoplasm might accidentally run into each other, and this could occur. That might be true. But what enzymes do is make improbable interactions more probable. These two molecules are not likely to come in contact with each other just randomly, but once bound to this enzyme, they're much more likely to come back and interact with each other. So that's one of the reasons enzymes are very important, is because they help facilitate unfavorable reactions. Now, in addition to it releasing these products here, I should have also included the fact that the enzyme returns to its normal shape. I did my best to draw it the same way, but it returns to its normal shape. I also want to go over some specific stages that your book talks about, and I want to do it by looking at this picture here. Your book summarizes this process of binding a substrate, a conformational change, and releasing it in these three steps. The first step here is initiation, whereby the substrates, it could be one or two in this case, or even more, that bind to this active site. And it's not just by accident that they bump in here. They are precisely oriented into this very specific site on the enzyme. The next stage is this transition state, facilitation. And that is the state where the enzyme changes its shape, provides that induced fit, and allows the enzyme to exist just for momentarily this different shape. And then finally, termination. That process by where the products are released and the enzyme returns to its normal state. All right, two more points I want to make on this slide. Now, enzymes, though I didn't show it here, and not all of them are readily this way, but they all can be reversible. In this particular case, this reversible reaction is a non-spontaneous reaction, so it's very unlikely to occur. The other thing I want you to note as you're looking at that, and that's looking at this enzyme that has just been released, and I want you to recognize that enzymes are not consumed. Meaning, they take one set of substrates and they turn it into one set of products. They're not immediately degraded and unusable. Rather, they can keep cycling back and get reused many, many times. So they are not consumed in this reaction. Now, up to this point, what we have said is that enzymes bind substrates and they turn them into products. But now I want to talk about why it is important that enzymes do this. So I'm going to erase this and move in that direction. Okay, so what I want to talk about now is that enzymes reduce the energy of activation. So let's talk about this energy of activation, and in doing so, let's draw this graph here. On this vertical axis, we have free energy, and down here we have time. And we can draw our curve like so. And we can use our same terms that we had on the previous slide, where we had glucose and ATP over here. These are the reactants. In order for them to be converted into glucose with a phosphate on it plus ADP, it has to use this much kinetic energy. And we call this energy here, we call that the activation energy. What we're saying is that it takes a lot of energy to get to this transitionary state. That state where we have the glucose and the ATP bound. The greater the activation of energy there is, the more stable this transition state is. And the more stable that transition state is, the less likely it is to form our products down here. So this is where enzymes come into place. Over here, this is, on the left, this is no enzyme. And on the right here, this is going to be with enzyme. We still have our same starting point of free energy, and we're still going to have our same ending point, which means that our delta G here, so this is delta G, even if I didn't say so, it's the change in free energy. So between here and here, that's our delta G. And that's going to stay the same with or without an enzyme. The change in free energy doesn't change. It's just the rate at which it will occur. So what an enzyme does is it lowers that activation energy. So over here we had this very high amount of energy that was required, and over here we have a much lower amount. And the reason it takes less energy in enzyme, because remember, over here, this transition state wasn't being facilitated by an enzyme, whereas over here it is. So this enzyme properly holds that glucose molecule and the ATP molecule in such a way that it facilitates the release of the products of glucose with the phosphate on it and ADP. It decreases the energy of activation, or the activation energy. Less kinetic energy is needed to convert a reactant to a product. And that's the purpose of an enzyme, is to make these very improbable interactions more probable. Now on your own, I want you to think about how we could achieve this lower energy of activation without an enzyme. What could we do to the environment in such a way that would make glucose and ATP more likely to come in contact with each other, that would also lower this energy of activation without an enzyme? Okay, now the next thing I want to talk about is the idea that enzymes don't always work alone. And in talking about this, I want to talk about three different things here. The first are cofactors, the next are coenzymes, and last are prosthetic groups. So cofactors are inorganic ions that bind to enzymes. I should also mention that they are reversible when they bind. They can come on and off. But when they bind, they somehow change the shape or change the activity of the enzyme to increase enzyme activity. Some examples of these would include magnesium or iron or calcium. Next, I want to talk about the coenzymes. What makes coenzymes different than cofactors is that coenzymes are organic molecules. They do a similar thing. They bind to the enzyme to increase activity. Now, some examples of these are molecules we'll talk about when we talk about respiration and photosynthesis, but NADH and FADH2. And remember, when I say organic, what I'm really saying is a molecule that contains carbon. But both of these serve a very similar purpose. They both bind to enzymes to increase their activity. And they're both reversible. I didn't mention that here, but these coenzymes are also reversible. Now let's go back to these prosthetic groups. These are molecules that permanently bind enzymes and increase activity. But the key difference here is the word permanently. An example of this is retinol. It binds permanently to a specific enzyme to affect the activity of that enzyme. All right, now I want to spend some time talking about factors that modify enzyme function. And in general, I'm going to talk about 4 different factors. They include temperature, pH, interaction with other molecules, and the last one is changing its primary structure. Even though these are all 4 different ways, let's remember that the way they're going to change the function of that enzyme is by and large by changing the shape of the enzyme. Temperature, pH, interactions, and changing this primary structure all ultimately change the shape of the enzyme, and so will modify its function. So let's first look at temperature and pH. So now let's think about specifically temperature and pH. How could temperature and pH affect an enzyme in such a way that it would change its function? Well, let's think of it this way. At least our prediction might be, is that at one temperature, our enzyme might look like this. And let's just make up a temperature. Let's say at 20 degrees Celsius, it looks like this. But at 37 degrees Celsius, different non-covalent interactions can occur in this protein to make it change its shape. And now let's say its shape is like this, where that active site now is more accessible to the substrates. In addition to the enzyme changing its shape, if we have, say, 2 substrates that are trying to bind with each other at one temperature, say at a colder temperature, their movement is going to be limited. But at a higher temperature, their movement is going to be bouncing around a lot more frequently, and as a result, they might more likely come in contact with each other. So combining the change in shape of the enzyme, but also the change in the movement of the substrate molecules, it's possible, at least the prediction would be, that they would be more likely to bind to the enzyme and get turned into a product. The same would be true of pH, because we know that pH values also change the structure of proteins. So say maybe at a low pH of say 2, and then a more neutral pH, say of 7, maybe we get a change in shape. Or it could go the other way too. I just made this up. It could have been pH 7 here and pH 2 here. But the idea is that these physical parameters, temperature and pH, can change the shape of a protein in such a way that it facilitates the activity of that enzyme. Now let's move on to our third factor that modify enzymes' function. And remember, this one was other molecules that bind to enzymes. And to talk about this, I want to talk about 3 examples. The first is competitive inhibition. The second is allosteric inhibition. Sometimes this would be called non-competitive inhibition, but we're going to call it allosteric. And also we want to talk about allosteric activation. Okay, let's begin with competitive inhibition. And let's draw our enzyme like so. Okay, now let's draw its natural substrate here. This is the substrate that is supposed to bind into the active site, and when it binds, it gets converted into some product. So a competitive inhibitor will resemble this natural substrate, but it'll look a little different. So it has this shape that will get wedged into this active site, but because it interacts in a non-natural way, it doesn't get converted into a product, but rather it just continuously occupies the active site, preventing the natural substrate from coming into the active site. Sometimes this happens because the competitor has a higher affinity for the active site compared to the natural substrate. Another way this could happen is that there is more of the competitor than the natural substrate. So if there's more of this competing substrate, it is more likely to bind into the active site than the natural substrate. We say it's competing because both of these are competing for the same site. Now, let's think about allosteric inhibition and allosteric activation. Up to this point, we've always drawn our enzymes in one way or another with an active site like so, but that's it. Sometimes there's other binding sites on the enzyme. So in this case, we have our natural substrate that wants to bind to this active site. But we can have an inhibitor over here that can bind to this other binding site. And when it binds to this other binding site, what happens is there's a conformational change of this enzyme in such a way that the active site closes up. or is no longer accessible to the natural substrate. Again, an inhibitor binds to a binding site other than the active site. In doing so, it changes the conformation of the whole protein in such a way that the natural substrate can't have access to the active site. So now let's think about allosteric activation, and that is the reverse of allosteric inhibition. So in this case, you start off with an enzyme where the natural substrate doesn't have access to it until this activator, now it's an activator, it used to be an inhibitor, but now it's an activator, it binds to this alternative binding site in such a way that it changes the conformation of the enzyme such that it now opens up the active site. Now it can bind into the active. And again, that's because our activator is now bound. So again, normally this enzyme isn't working, but our activator substrate binds to this other binding site. When it does that, it changes the conformation in such a way that it opens up the active site to allow the substrate to bind to the active site. The last thing we want to talk about are changes to the primary structure. So what we're really talking about here are adding covalent bonds. A very common way to do this is by using phosphorylation. Adding a phosphate group to the enzyme that changes the shape of the enzyme or the charge of the enzyme to facilitate the activity of the enzyme. So for instance, we could have our enzyme here, and the substrate that wants to bind, let's say it has a positive charge on it. It may still be able to bind into this active site, but not as strongly as if we could have a negative charge here. And one way to add a negative charge here is to add a phosphate group, which is negatively charged. Maybe we'll add several negative charges, which will allow this positively charged substrate to come into this active site, and not just because it fits in there, but because it's able to establish these ionic bonds with these phosphates that it wasn't able to do before. So again, in this case, we're adding phosphate groups here as a way to change the charge and probably also the shape of the protein, or the enzyme I should say, so that a substrate that has positive charges can interact with the active site with a little bit stronger interactions. Okay, the last thing I want to talk about here is metabolism. We just spent quite a bit of time talking about enzymes and how they carry out different reactions. In the podcast before, we talked about energy and how it was important to consider available energy when thinking about cellular reaction. All of that is important for the metabolism of a cell. So let's first give a brief definition of metabolism. We can think of metabolism as the sum of all chemical reactions that occur in a cell, or you could say in an organism, but we're going to focus on the cell. So these reactions are going to be a combination of reactions that build things up and a combination of reactions that tear things down. So for instance, if we start with food that we might eat for lunch or some other meal, that is going to be broken down into building blocks. So the proteins we eat are broken down into amino acids. So we can use that as an example here. We could have easily said the polysaccharides we eat can be broken down into monosaccharides. Lots of examples. Now we call the reactions that break down larger molecules into smaller molecules, we call those catabolic reactions. As they break food molecules down into these building blocks, they will also release heat and energy, going from an ordered structure like the food to a non-order. So following the second law of thermodynamics. So these would be more exergonic reactions. Now these building blocks can go on to make molecules in the cell. They're going to use this energy that's created in these catabolic pathways to build these molecules. So for instance, these amino acids are going to now be used to make proteins. These pathways that build things, larger molecules, we call anabolic reactions. The way I've always remembered these is I think of anabolic steroids, and anabolic steroids help build muscles. And so anabolic reactions are going to help build larger molecules. Now, as we're looking at this, and as we move forward with this semester, and you move forward with your other classes, it's important to remember that these pathways, either the catabolic or the anabolic, don't just occur all the time. They're highly regulated. And a common way to regulate these pathways is using something called feedback inhibition. And so I'm going to erase this so we can talk about feedback inhibition. Okay, so let's consider a generic enzymatic pathway here. And we'll start with enzyme 1. And we'll draw a couple of other enzymes here. And they each have their own active sites here. Alright, so enzyme 1 will bind a substrate like so. And when it binds here, it is enzymatically converted to a product. And let's just say that product that it produces is this product. And now this product will serve as a substrate for enzyme 2. And it binds into the active site of enzyme 2. And upon doing that, it is converted to this product here. And this product will now bind into the active site of enzyme 3. Upon doing that, it will release a product, let's say, that looks like this. This product is important in building something for the cell, but once it accumulates to a certain concentration, the cell determines it no longer needs any more of this product being made. This is the ultimate product that this pathway is trying to create, and now the cell has enough of it. So once it has enough of it, it can send some of these molecules back here to the first enzyme where it will bind this alternative binding site. In doing so, it will cause a conformational change of enzyme 1, blocking this enzyme, this active site, and now this substrate can no longer bind. If this substrate can no longer bind to enzyme 1, we've effectively stopped this pathway, because enzyme 2 needs the product of enzyme 1, enzyme 3 needs the product of enzyme 2. So by blocking enzyme 1, we block the whole pathway. And remember, the reason enzyme 1 is blocked is because the pathway at one time was working and producing a lot of this final product. And then the cell said, I have enough of this product, let's shut down this pathway. Now, over time, what will happen are that these products here will start to get used up by the cell. And when that happens, it will no longer bind to this active site, this alternative site of enzyme 1, which will now, once again, open up this active site, and the pathway can be resumed until you get to the point where you have too much of this enzyme product here, the final product here. So again, this is called feedback inhibition, and it's a very common feedback mechanism we see throughout cell biology that you'll come back to time and again throughout your studies. So that's all I have for today. So let's close with a quick summary. We spent a lot of time talking about enzymes. We talked about the active site, substrates, induced fit, which was caused, remember, by non-covalent interactions. We talked about how enzymes lower that energy of activation. We talked about how sometimes enzymes bind other molecules to affect their activity. And in that we talked about coenzymes, cofactors, and prosthetic groups. We then talked about the regulation of enzymes. In that discussion we talked about temperature, pH, inhibitors, and activators. And then we talked about phosphorylation. And then we closed with metabolism, where we talked about anabolic and catabolic reactions and how together they will balance all the reactions in the cell to build things and to break things down. And then we closed with the final discussion on feedback inhibition as it's related to metabolism, how whole pathways are regulated. Okay, that's all I have for this podcast. If you have any questions at all, please let me know. If not, I'll see you in class. Bye.